Yeah.
Great. Hello, everyone. I'm Congyao Zhang, a postdoc at the University of Chicago. Today, I'm going to talk about shocks and the splashback in class Outskirts. So this figure shows you an X-ray view image of hot gas in large-scale structures. So you can see actually a large fraction of this gas is in the outskirts of halos. And if we zoom in onto one galaxy cluster, we'll see that actually its hot intergalactic medium is covered by a strong external shock. And the morphology of this shock is actually not spherical, but shows this kind of blossom-like morphology. And more quantitatively, from cosmological simulations, we can see the radius of the external shock of intergalactic medium is generally 2 times larger than the splashback radius of dark matter halo. And the splashback radius generally characterize the size of dark matter halo. So, but this result is surprising because it's contradictory to the prediction from self-similar spherical collapse model. This bottom left panel shows you an example of the self-similar solution. The black and red solid lines show you the dark matter and gas density profiles. You can see in this self-similar solution, their boundaries are very close to each other. And the radius of the boundary is a function of the so-called smooth mass accretion rate, gamma s. And in the self-similar solution, when gamma s is higher, the radius of the boundary of the cluster is smaller. So now the question is why there is a big discrepancy between the self-similar model and the numerical results. So in my talk today, I will try to convince you that this is caused by merger process, which is missing in the self-similar solution. And here in these 4 panels, I show you an example of merger between 2 galaxy clusters. And in this case, a subcluster, smaller subcluster moves into the main cluster from the top left. This black solid dashed line represents the trajectory of the subcluster. And the black arrows mark the positions of merger shocks. So you can see actually after crossing the epicenter, the subcluster starts to fall backwards towards the center of the main cluster. But in the meanwhile, the merger shock always all the way move to larger cluster radius. So you can see actually in the 3rd and 4th panels, the distance between the outer boundary of subcluster and the shock front becomes larger and larger. So in this process, the merger shock experiences a transition from a ball shock to a runaway shock. And an important property about the runaway shock is that once it's formed, its propagation is mainly determined by the surrounding atmosphere, but not the subcluster. So for this reason, the runaway shocks could be long-lived while moving down a steep gas density gradient. And in our study, we found that generally speaking, if the gas density profile of the atmosphere is deeper than R2-3, the runaway shocks could maintain their strength over a large distance. So this is a theoretical prediction. And in this red panel, I show you some observations. These solid lines show you the slope of gas density profiles as a function of cluster radius measured in X-ray observations. So you can see generally beyond R500, the slopes are close to -3 and even reach up to -4. So this observational results suggest that there is a habitable zone populated by runaway merger shocks exist in the outskirts of galaxy clusters beyond R500. And the runaway shocks in this habitable zone are actually good candidates of generating radio relics found in the periphery of galaxy clusters. And another interesting property of runaway shock is that it shows N-shaped waveform. Looks like this, a leading edge trailed by rarefaction, and there is also another, the secondary shock front. And here, this top panel illustrates how such an N-wave structure is formed during the propagation of the runaway shock. I think a direct consequence of such N-wave structure is that the radio emission, strong radio emission from the runaway shock is always confined within a narrow radio shell just behind the shock front. That's because the gas is always rapidly decompressed in the rarefaction. And such a structure, generally, such a feature is consistent with the geometry of radial relics found in the class Outskirts. And I think an interesting real example of the runaway merger shock is shown in the coma cluster. The runaway shock driven by the unfolding group in GCF2021 is moving somewhere here, associated with the radial relic, shown as the green contours in this figure. Here, I do not have much time to discuss more details. If you're interested, please check Natalia Liskova and Eugene Trozov's recent papers. And what I want to say is that this is not the end of the story. We know that once after detection from subcluster, the runaway shock will continuously move in the class Outskirts until it encounters the accretion shock at the boundary of the interclass medium. So what's going to happen when the runaway shock collides with the accretion shock? And generally speaking, three discontinuities will be formed: forward shock, a rarefaction, and the contact discontinuity in the middle. So in this talk, I will mainly focus on the forward shock. We call it merger accelerated accretion shock, the MA-shock. MA-shock is interesting because it's powered by a merger, but not the accretion. But at the same time, the MA-shock has very high Mach number, higher than the pristine accretion shock. So it's up to a few hundred to even 1,000. And so in our study, we try to model the formation of MA-shock and to see how the MA-shock could affect the evolution of the entire galaxy clusters. So to reach this goal, we run idealized merger simulations between two galaxy clusters, but in a cosmological background. And we initiate each cluster by a sub-similar solution. So in this way, actually the smooth accretion shock, splashback feature of dark matter halo are all automatically included in our model. So here I'll show you an example of our major merger simulation. So from the left to right panels, it shows the evolution of dark matter density, gas density, and temperature slices. So here, let's firstly see the evolution of dark matter distribution. This top left panel shows you the inner condition of our simulation. So you can clearly see the outermost caustic surface for each cluster. And when these two clusters are approaching each other, actually this caustic surface could even be preserved in the early phase. And when the two clusters are sufficiently close, the merging system experiences a rapid contraction. And at this moment, the splashback radius of the cluster is even close to the virial radius of the system. And after about 1 to 2 gigayears after the pericentric passage, the genuine caustic surface starts to recover. And in this figure, I show you the evolution of the splashback radius in units of virial radius. Different lines show you the mergers with different merger mass ratios. So you can clearly see in major mergers, there is a significant contraction. And near the pericentric passage, the splashback radius could reach to the virial radius. And in the bottom panel, I show you the corresponding evolution of the total mass accretion rates of the merging system. Here, a key point I want to show is that the total mass accretion rate actually contains two components. One is from the smooth accretion, characterized by the smooth mass accretion rate, gamma s. Another part comes from the merger. So it means the total mass accretion rate of the system could be much larger than the smooth mass accretion rate input in the simulation, especially near the pericentric passage. And the evolution of the splashback radius depends on the evolution of total mass accretion rate, which reflects the deepening of the gravitational potential. But later you'll see that the evolution of the shock radius is very different, which depends on the local smooth accretion rate. So that's why there could be a large offset between the shock radius and the splashback radius. And here I show you the evolution of the gas. These panels show you the pre-merger stage. So you can see when two clusters are approaching each other, the gas between them is significantly compressed. Various shocks and contact discontinuities could be formed in this process. And right after the pericentric passage, a pair of bow shocks are formed. And as I discussed above, these bow shocks will gradually detach from the merging clusters and turns to be the runaway merger shock. And eventually this runaway merger shock will overtake the accretion shock at the boundary of the intercluster medium and form the MA-shock. In this figure, it's marked by the yellow arrows. So you can see once MA-shock is formed, the gas atmosphere of the merging system is significantly expanded. And I would say in cosmological simulations, most of the strong external shocks are actually the MA shocks, but not the ordinary accretion shock. And here I show the evolution of the shock radius and splashback radius in red and blue curves. Top panels show you the result from major mergers, but with different merger configurations, and bottom panels show you minor mergers. So you can see, and all these simulations here use the same smooth max accretion rate, which is 1. You can see in major mergers, there could be a large radius of sight between shock and splashback feature. The ratio is around 1.5, and this offset is less prominent in minor mergers. In our simulations, we also see that this radius offset is very sensitive to the smooth mass accretion rate. When the gamma is high as 3, these two radii are very close together. So similar to the prediction from self-similar model, because in this case, the cluster growth is dominated by smooth accretion, not the merger. But when the gamma S is small, especially smaller than 1, the shock radius could be much larger than the splashback radius. So I think these simulations demonstrate that mergers could easily generate strong radius offset between the shock and splashback feature. And because in cosmological simulations along non-filamentary direction, we do see such a large radius offset. So it implies that along these non-filamentary directions, the smooth mass accretion rate of the merging system is very small, smaller than 1, even though the total mass accretion rate of the system can be much larger. And another interesting point here is that in our simulations, we do see 3 types of contact discontinuities. And this is my last slide. Once MA-shock is formed, a fraction of gas is distributed beyond the virial radius, which plays an important role in run pressure stripping in falling galaxies. And the efficiency of such process is sensitive to the mass ratio between the infalling galaxies and the clusters. I think I will leave my conclusions here. I'm